I'm Amit Pathak. I'm currently working at the Department of Physics, Banaras Hindu University, Varanasi. It's a traditional city. I'll say that it's a very traditional city in northern India, and hope you get a chance. Everybody, all the participants get a chance to visit sometimes. So what I work on is interstellar PAHs. PAHs are basically polycyclic aromatic hydrocarbons, basically fused benzene rings. So an example is given here at the top of this slide. So this example is of coronium. So the important thing about PAHs is that they are found everywhere. They are actually present in the terrestrial environment. They are supposed to be present in several kinds of interstellar environments. So my research area I've been working on PHs like for the last more than 15 years now. And mostly my interest is spectroscopic studies of various variants of PHs. Okay. I also am interested in some modeling, astrochemical modeling of other molecules as well. Plus, I also have done some UV spectroscopy, but here I'll be talking mainly about interstellar polycyclic aromatic hydrocarbon molecules, PHs. Okay. So in this, I have several collaborators who have been working with me. Midusmita was my PhD student. Currently, she is a JSPS postdoc at University of Tokyo. Other collaborators from University of Tokyo include Dr. Itsuki Sekon and Professor Takashi Tanaka. Then my current PhD student Ekant works at Banaras Hindu University. Another postdoc I was previously at Tezpur University, so there a postdoc at Tezpur University, and Professor Peter Saar at University of Nottingham. So this is why PHs are actually, important. PHs are very, very stable. Okay, so anything which is present in the interstellar atmosphere, interstellar medium, has to be very, very stable because it has to undergo radiation from stars, cosmic rays, and all sort of things. So PHs are very stable. Why they are stable? Because the electrons there in the PHs are delocalized. They are sooty molecules. Sooty in the sense, if you burn a hydrocarbon, automatically it will form some sort of pH molecule. Okay, so pH is not a single molecule, it is a family of molecules consisting of fused benzene rings. So here in the picture you can see this is an example of two benzene rings which are fused. It is known as naphthalene. PHs are very, very carcinogenic. They cause cancer, skin cancer, lung cancer if you inhale. So even if you smoke, the smoke contains PHs. Vehicle exhausts contain PHs. Wherever hydrocarbon burning is going on, you'll have PHs. They are carcinogenic. So experimentalists actually who are working on the spectra of PHs, who are synthesizing PHs, have to handle it very, very carefully because they are highly cancerous. So why are we interested in interstellar perspective of PHs? Why interstellar implications of PHs? Because there are several unsolved problems in the interstellar medium, and PHs might be very significantly contributing to at least some of them, and maybe slightly less significantly, but an important contribution to few of them. So the first is aromatic infrared bands. Aromatic infrared bands are emission bands seen towards interstellar sources, diffuse sources, not towards stars. Okay, so diffuse environments. So these bands are placed at 3.3 micron. The important ones I'm telling: 3.3 micron, 6.2 micron, 7.7, 8.6, 11.2, and so on. Actually, there are several weaker ones as well. I'm just telling you about the important, the most intense ones. Then there is a UV bump at 217.5 nanometers or 2175 angstroms. This bump you can see here. This is the interstellar extinction curve, and there is a bump at 2175 angstroms. This bump is still unexplained, and several suggestions are there suggesting it is coming from graphite or other things. But PHs might also be contributing to the existence of this bump. Then there is 3.4 micron absorption feature. This far UV rise of the interstellar extinction curve is is also said to be coming because of the pHs. Then the extended red emission. The extended red emission is like plateau seen towards some sources, which extends from like 5,500 angstrom to 6,500 angstrom. So this whole bump is coming from say pH dications or something like that. Then there are several hundred diffuse interstellar bands. Diffuse interstellar bands are absorption features seen on the interstellar extinction curves, mostly in the visible. You can see from red to blue. You have a lot of these diffuse interstellar bands. We also have some in the near IR, and so at least two of them have been recognized due to fullerene cations. But fullerene is what? A buckyball made of pentagon and hexagon rings. So fullerene, if fullerene breaks down, then it might create pHs, or even pHs may help in the formation of fullerene cation. So in some way, the pH molecules might be contributing to the diffuse interstellar bands as well. Okay. So my main interest is basically in the aromatic infrared emission bands. These are emission bands which are seen in the mid-IR region. These bands actually are due to the vibration of bonds in pH molecule. Okay, so a bond basically maybe bond maybe CC bond. A pH molecule is fused benzene rings, so it will contain CC bonds. It will contain CH bonds. So the vibration will be of CH. So we can have CH stretch vibrations. We can have CH out of plane, in plane vibration. We can have CC vibration, CC stretch, CC in planes. So such vibrations will give rise to these emission features. So what actually happens? So a pH molecule may absorb a UV photon which comes say from any star, and then it will get excited and it will relax through IR fluorescence, and vibrations will take place, giving rise to emission bands at several positions. Okay, so this is for a pH cation. You can see the absorption is taking place. It goes to a higher excited state, and then it crosses over, and then this is IR emission. It's a cascade emission basically, and each of this cascade is giving rise to IR photons. Okay, so recently I've been working on several variants of pHs. Like if you introduce a deuterium instead of say hydrogen, if we attach aliphatic rings to a pH molecule, if we dehydrogenate a pH molecule, or if we introduce a nitrogen inside a pH molecule. So one by one I'll be discussing these. So so the deuterated pHs, actually these are ISO observations reported by L. Peters 2004, and they actually show that there are features at 4.4 micron and 4.65 micron which might be coming because of deuterium in pHs. So this is a pH molecule. It has, instead of H, it has a D. So this is an aromatic CD bond, and here we again have a D, but this is an aliphatic CD bond. Okay, so the aromatic CD stretch vibration is giving rise to a feature at 4.4 microns, and the aliphatic CD stretch vibration is giving rise to a feature at 4.65 micron. Okay, this is another observation by Onaka et al. In 2014 using Akari data. They actually looked at a very narrow part of the earlier object, the same object actually they looked at, but they pinpointed it, and they found that these features actually are very, very faint. The 4.4, 4.65 micron features are very faint in. Okay, so they suggested that if at all deuterium is present in pHs, it must be present in very, very large pH molecules. Okay, so we actually gathered some interest, and we started studying the spectra of the deuterated pH molecule. So why it is interesting to have deuterium in pH molecule? It is interesting because deuterium is depleted in the interstellar medium. It is not, some deuterium in the present interstellar gas is missing compared to the primordial abundance. And this is not actually explained by the nuclear fusion reactions, astration actually, which is going on inside stars. So, and there is no, if at all the deuterium is getting fused in stars, then it should give rise to oxygen. So there should be an anti-correlation, which is not seen actually. So that means the nuclear fusion reactions are not responsible for the missing deuterium. So deuterium must have gone in depleted in interstellar molecules or interstellar solids grains. So one such case may be that in deuterium is now present in interstellar pHs. So we looked at this is a coronine molecule, and what we did was we replaced one of the hydrogen with deuterium, and then we also created aliphatic CD bonds. So we created aromatic CD bonds. We also created aliphatic CD bonds. And what we found was the same result. The aromatic CD bonds actually give rise to 4.4 micron features, and aliphatic CD bonds give rise to 4.7 micron features. The aliphatic CD, I mean, deuterium, we called it deuterated coronine, and the aliphatic one we called it deuterinated pHs. Okay, and these are what we have studied is in, I mean, we have ionized the pH. We have removed one electron from the pH molecule. So what actually is happening is we have this is a coronine molecule, and if we have say two H's, CH, CH, aliphatic CH here, it gives rise to a band at 3.4 micron. But if one of the H is replaced by D, the whole peak actually splits into two. One is CH stretch, aliphatic CH stretch, and this is aliphatic CD stretch. And the intensity is, I mean, this is amazing that the intensity also is almost equally divided. Okay, so this is what we are seeing. This is a band at 4.6, 4.7 micron CD stretch, which is very close to the 4.65 micron, which is seen in observations. So we studied several of these pHs, and we created a scaled D by H ratio. And what we found was that the ratio which comes from observations is actually matching with a large pH molecule, circumcoronine, which has about 54 carbon atoms. Coronine has 24 carbon atoms. So compared to coronine, this is a very large pH molecule. So this the D by H ratio is matching very well here, and this is the same thing plotted here. So we see that this is the number of carbon atom in the pH molecule. You see that the observed ratio suggests that 0.1 to 0.3 D by H ratio should be there. The observations actually are suggesting this, and we find that large pHs actually match very well to the observations. I'll skip this slide. Then aliphatic pHs. So aliphatic pHs are, I mean, basically we attach some aliphatic molecule with the pH ring, replacing one of the hydrogens. What we see is we start seeing, so the aromatic CH stretch gives rise to 3.3 micron band. If we attach aliphatics here, we start seeing peaks at 3.4, 3.5 microns. Okay, so the black lines are from neutrals, the red ones are from pH cations, and the gray areas you see are observations. You see that I mean, we do not match exactly. These are theoretical results, and we do not expect the theoretical results to be sitting on the observation, the gray areas, but they are quite close to that. Okay, so the aliphatics actually are helping, but here you see that nothing is there. Okay, so these kind of aliphatics may be taken off, but some of the aliphatics actually match very well, like this one. But we have to understand that if we attach aliphatics to pH molecules, the aliphatics are sorry, the aliphatics are less stable compared to pHs, because pHs have aromatic structure and the electrons are delocalized, which is not so in the aliphatics. So aliphatics maybe the CC bond or the CH bond may easily break in aliphatics, but we see quite a match with the observations. Dehydrogenated pHs. So dehydrogenated pHs are important. Why? Because once you have these, this is a huge pH sheet of dehydrogenated pH. When all the hydrogen atoms are taken off, what may happen is that one of the rings, one of the CC bonds may break, and it will start forming pentagons. You know, five ring structures. Okay, when five ring structures start, are being created, then the whole sheet, which was planar initially, starts curling up, And this curling may result in the formation of buckyball C60 fullerenes. Okay, and fullerenes it is already known that fullerene cations are present in the interstellar medium. So dehydrogenated pHs may play an important role actually in the formation of fullerene cations. So we actually studied this Coroni, this again Coroni. We started taking off hydrogen one by one. What we started seeing was that coronine, you can see on one ring there are two hydrogens attached. On every ring there are two hydrogen atoms attached. If you remove one of them, then only one of the like here, for example, this case, this top hydrogen is taken off. So we have only a single CH bond here on this ring. This single CH bond, when it starts vibrating, CH stretch, it doesn't give rise to a 3.3 micron traditional band, but it gives rise to 3.4 micron feature, which is surprising for us. And then we start seeing a new peak at 5.2 micron feature. This is 5.2 micron. 5.2 micron feature also has been seen in observations, but it was explained by some other pH molecule. But we also see this feature in dehydrogenated pH anions. Okay, one electron is added to this. So this again is an important result of this. So this, I mean, presence or absence of this feature may tell us about up to what, I mean, how many hydrogens have been removed from a big pH molecule. The scale of dehydrogenation here. Okay, nitrogenated pH. So if you see the pH molecules, the blue dots are basically the carbon atoms have been replaced by nitrogen. So we have a nitrogen here, which is called exonitrogen. This is an endonitrogen inside carbon inside the ring has been replaced. So the surprising result here is that in observation, this is an observation, which generally observations show very strong 6.2 and 7.7 micron features, while the 11.2 and the 3.3 micron features are less intense. Okay, they are, but here this is a planetary nebula where we see very strong 11.2 along with 6.2 micron feature. Okay, so this actually is explained by nitrogenated pH molecules, which is a very, very important result here. Okay, so I'll end my talk. So pH, I mean, the existence of pH molecules in the interstellar medium is actually established, but not a single pH molecule has yet been detected. So this is an open field in astrochemistry, and people are, I mean, spectroscopists, astronomers, chemists, physicists, they are all working hard to actually detect a single pH. The problem in detection is that these pH molecules are highly symmetric. They do not show any kind of rotational features which can be detected by, say, radio astronomy. They only, I mean, their features are detected only by vibration. So CH vibration, for example, it comes from a family of pH molecules. So you cannot pinpoint that, no, this is coming from coronine or ovaline, or I mean, single pH molecule cannot be pinpointed. So this is a problem, but dedicated observations and experiments and more theoretical things, I mean, details are needed to just confirm the presence of, at least to pinpoint a single pH molecule. Okay, and I'll acknowledge funding from JSPS, DST, UK, India Education Collaboration, and Views HPCs at Nottingham, IUCA in India. Thank you very much for listening. Any questions will be welcome.